Reality is not what the human mind believes it sees. What we call the world is already a translation, a model, a fragile attempt to grasp something far deeper than perception allows. For centuries, humanity trusted its senses. The sky looked still. Time seemed to flow the same for everyone. Space appeared solid and unquestioned. Yet one thinker dared to confront this quiet certainty. He asked a question that philosophy had whispered for millennia, but science had rarely faced directly. What does the human mind truly know about reality? Before modern physics reached its confidence, and long before technology convinced people that knowledge had conquered the universe, Albert Einstein was already dismantling the illusion of certainty. Through his exploration of time, space, and the structure of the cosmos, he did more than propose equations. He exposed a deeper philosophical tension between the world itself and the models we build to understand it. Before we continue, you are gently invited to subscribe, leave a like, and share a comment. This channel is a small space for grounding and reflection, created for those who seek a calmer way of understanding themselves and the world. If you feel comfortable, tell us where you are and what time it is for you. Your presence here matters, and your words help weave a quiet community across the distance. May what follows bring you ease, clarity, and a softer place to rest your thoughts. Einstein's revolution was not merely scientific, it was existential. He revealed that what humans call reality is never observed directly. The mind constructs frameworks, corrects them, and replaces them again. Science itself becomes a continuous act of doubt. But this realization opens a far more unsettling question. If perception is limited, and theories are only models, then what is the true structure of the universe that hides behind them? To approach that question, we must begin with the first fracture in certainty, the moment when perception itself becomes suspect. Human perception is not reality. It is only a fragile construction the mind erects in order to survive the chaos of existence. This is the first wound that philosophy opens. We believe we see the world. We believe our senses deliver truth. Yet what we actually possess is only interpretation, a mental model assembled from fragments of light, memory, expectation, and fear. Before modern neuroscience began mapping the brain, before cognitive science spoke about models and simulations, one of the greatest scientific minds had already sensed the fracture hidden inside human knowledge. Albert Einstein did not merely investigate equations. He confronted a deeper question that philosophy has asked for thousands of years. What do we truly know about the world that surrounds us? The problem appears simple. It is not. The moment we examine perception carefully, certainty begins to dissolve. Human beings never encounter reality directly. Light reaches the eye, signals travel through nerves, the brain constructs a picture. What we call the world is therefore not the world itself. It is the brain's best attempt to organize incomplete information. This claim sounds radical, but its structure is unavoidable. First comes the philosophical rupture. The mind does not mirror reality. It compresses it. The universe is immeasurably complex, yet the human brain must reduce that complexity into manageable patterns. Without simplification, we would collapse under the weight of raw information. Explanation follows immediately. Every act of perception is therefore a negotiation between the external world and the internal architecture of the mind. We do not see what exists. We see what our nervous system allows us to construct. Evidence is everywhere once the illusion cracks. Colors do not exist in the universe as we experience them. They are interpretations of wavelength. Sound does not travel as melody. It travels as vibration. Even the solidity of objects dissolves under physics into fields and probabilities. What appears stable is already translation. The implication is brutal. Human certainty rests on filtered signals. We move through life believing we stand on solid ground, while our knowledge is assembled from approximations. Einstein recognized this tension early in his intellectual life. As a young thinker, he asked a question that quietly destroys naive realism. If the human mind constructs models of the world, how can we know whether those models truly correspond to reality itself? This question did not weaken science. It gave science its true purpose. Science is not the discovery of absolute truth. Science is the continuous correction of human misunderstanding. This statement demands confrontation. Most people treat science as a repository of facts. But facts change. The history of knowledge is a graveyard of confident errors. Each generation believes it finally understands the universe, only to watch its certainties collapse under deeper investigation. Consider the centuries before modern physics. The world appeared obvious. Space was fixed. Time flowed uniformly for everyone. Objects possessed definite positions. The cosmos seemed orderly and transparent. Then the ground began to move. Einstein revealed that time itself bends with motion and gravity. What one observer calls simultaneous, another observer may experience differently. The simple stage on which reality seemed to unfold suddenly became unstable. But the deeper revolution was philosophical. Einstein understood that theories are not mirrors of reality. They are conceptual frameworks that allow the mind to organize experience. A scientific theory is therefore not a photograph of the universe. It is a map drawn by human reasoning. Maps can guide, maps can clarify, yet every map simplifies the terrain. This insight reshapes the meaning of knowledge. The first branch of the argument emerges here. Perception produces models, not direct access to truth. The mind compresses the universe into manageable structures. Without this compression, there would be no understanding at all. The second branch follows immediately. Because our knowledge is model-based, every theory remains provisional. What appears complete today may tomorrow reveal hidden contradictions. The third branch completes the structure. Progress in science is therefore not accumulation of certainty, but refinement of approximation. Each stage exposes the limits of the previous one. People often misunderstand this process. They imagine that scientific revolutions occur because new data suddenly appears. But data alone rarely produces transformation. Information requires interpretation, and interpretation requires imagination. Einstein himself emphasized this with disarming clarity. Observation cannot by itself generate theory. The mind must dare to construct conceptual structures that go beyond immediate perception. In other words, knowledge demands creative courage. Why does this matter for human existence? Because the same mechanism that governs science governs everyday consciousness. We live inside mental models. The world you believe you inhabit is partly external reality and partly psychological architecture. Your expectations shape what you notice. Your fears shape what you interpret as danger. Your memories alter what you believe is possible. The mind quietly edits the universe. Modern life often pretends that technology has solved the problem of knowledge. We possess satellites, data streams, algorithms. Information flows faster than ever before. Yet the fundamental condition of human understanding remains unchanged. We still interpret through models. In fact, the modern world intensifies the illusion of certainty. Digital systems create the impression that information equals truth. But information is only raw material. Meaning still emerges from interpretation, and interpretation remains vulnerable to error. Human beings therefore face an existential tension. We long for certainty. The mind craves stable ground, but the structure of knowledge denies absolute foundations. Our understanding of the universe evolves through correction, revision, and intellectual risk. Einstein's intellectual courage lies precisely here. He did not cling to inherited frameworks. He questioned the assumptions hidden inside them. This willingness to doubt perception becomes the beginning of freedom. Yet it also exposes a deeper psychological discomfort. Why do humans resist the idea that perception is limited? Because acknowledging this limitation threatens our sense of control. If our view of the world is incomplete, then the security we feel may also be fragile. The mind therefore prefers illusion to uncertainty. Inside every individual, there exists a quiet struggle between two forces. One force demands stability. It wants a world that is predictable, understandable, fixed. The other force demands truth. It pushes us to question what appears obvious. Philosophy begins when the second force refuses to remain silent. Einstein embodied that refusal. He examined the basic assumptions behind space, time, and observation. Instead of trusting perception, he interrogated it. Instead of accepting inherited frameworks, he dismantled them. This act of intellectual rebellion reveals something essential about human consciousness. Understanding is not passive reception. It is active construction. Every scientific theory represents a mental architecture designed to explain experience. Some architectures prove stronger than others. Some collapse under pressure. But none escape the fundamental condition that produced them. They are built by human minds confronting an immense universe. This realization leads to a difficult question. If perception is mediated and theories are models, can we ever claim to know reality itself? Einstein's answer was both humble and defiant. Absolute certainty may remain unreachable, yet the human mind possesses a remarkable capacity to approach deeper coherence. Each improved theory reduces contradiction. Each conceptual breakthrough clarifies hidden structure. Truth may not be fully captured, but it can be pursued. That pursuit defines the scientific spirit. Notice the existential dimension hidden inside this idea. The search for knowledge mirrors the search for meaning. Both require confronting uncertainty. Both demand the courage to question comfortable beliefs. And both reveal that progress emerges from doubt. Modern individuals often experience anxiety when certainty disappears. But Einstein's perspective transforms that anxiety into intellectual momentum. If our understanding is incomplete, then exploration becomes necessary. Ignorance becomes the engine of discovery. This psychological transformation matters profoundly. Instead of fearing the limits of perception, the thinker uses those limits as motivation to refine the models through which the world is understood. Science becomes an ongoing dialogue between mind and reality. A symbolic figure captures this condition clearly. Imagine a solitary observer standing beneath the night sky. The stars appear fixed and distant. To the naked eye, the cosmos looks calm, almost eternal. Yet the observer knows something deeper. Those points of light are moving, evolving, collapsing, exploding across incomprehensible distances. The peaceful image above is already an interpretation shaped by human perception. The observer, therefore, faces two worlds simultaneously: the immediate sensory world and the conceptual universe revealed by reason. Between those two worlds lies the true drama of human knowledge. Einstein lived inside that tension. His work did not simply produce new equations. It exposed the gap between appearance and structure. The universe revealed by physics often contradicts what the senses report. Time stretches, space curves, simultaneity dissolves. The comfortable stage of everyday perception begins to fracture. Yet, this fracture does not destroy meaning, it deepens it. Because once perception is questioned, the mind becomes capable of imagining realities that lie beyond immediate experience. Thought experiments emerge. Conceptual leaps become possible. The intellect begins to explore structures that cannot be seen but can be understood. And from this act of imagination, another force quietly enters the story. Reason alone does not generate revolutionary insights. Data alone cannot produce conceptual transformation. Somewhere inside the process of discovery, a different faculty awakens. The faculty that allows the mind to leap beyond observation itself. Imagination is not the enemy of science. It is the engine that drives it forward. This statement cuts directly against the comfortable myth that knowledge grows from data alone. People often imagine science as a slow accumulation of measurements, as if truth patiently emerges from observation. But history reveals a far more unsettling structure. Facts do not organize themselves. Numbers do not generate meaning. Data waits in silence until the human mind dares to impose a vision upon it. The leap always begins inside imagination. Long before laboratories confirmed his ideas, Albert Einstein had already understood this secret architecture of discovery. While many scientists treated observation as the supreme authority, Einstein quietly insisted on something more radical. The decisive breakthroughs of science are born not from measurements, but from conceptual daring. This insight reveals the second fracture within human knowledge. Reason alone is insufficient. Observation alone is blind. Between them stands intuition, the mysterious faculty that allows the mind to glimpse structures that are not yet visible. Consider the tension carefully. The first movement of scientific discovery begins with a claim. Reality does not reveal its deepest patterns directly to observation. The surface of the world is often misleading. Phenomena appear chaotic, fragmented, disconnected. If we relied only on raw perception, the universe would remain an incoherent collection of events. Explanation follows immediately. The human intellect, therefore, performs an act of construction. It proposes hidden principles that organize the apparent chaos. These principles are not extracted mechanically from data. They are imagined first and tested later. Evidence appears throughout the history of science. The most transformative theories were initially acts of conceptual courage. They began as intellectual visions rather than empirical conclusions. Einstein himself demonstrated this process with striking clarity. As a young thinker, he did not begin with telescopes or complex experiments. He began with thought experiments. He imagined situations that could never occur in ordinary life. He asked questions that seemed almost absurd. What would happen if a person could travel alongside a beam of light? What would time look like if two observers moved at different speeds? What if gravity were not a force, but a geometric property of space itself? These questions did not arise from new measurements. They emerged from imagination. And yet, imagination alone does not create science. The structure of discovery requires a second force. Reason must discipline intuition. Imagination proposes possibilities. Reason examines whether those possibilities remain internally coherent. If contradictions appear, the theory collapses. If the structure holds, the theory becomes a candidate for truth. This delicate balance defines the architecture of scientific thought. The first branch of the argument emerges here. Data does not produce theory. Observations can reveal anomalies, but they cannot, by themselves, invent explanatory frameworks. The mind must generate the conceptual structure that organizes those anomalies. The second branch exposes a common misunderstanding. Many people assume that imagination is opposed to rational thinking. In reality, the opposite is true. The greatest scientific breakthroughs require imagination guided by rigorous logic. The third branch delivers the philosophical conclusion. Science progresses not by abandoning imagination, but by refining it through disciplined reasoning. This synthesis reveals why Einstein placed such importance on creative thought. He once suggested that imagination is more important than knowledge. The statement appears provocative, even reckless, yet its deeper meaning is precise. Knowledge describes what we already understand. Imagination explores what might still be hidden. Without imagination, knowledge becomes stagnant. The modern world often forgets this lesson. Contemporary culture worships information. Data accumulates endlessly. Statistical models multiply. Algorithms process enormous quantities of evidence. Yet, the fundamental act of conceptual creation remains irreducibly human. No machine has yet replaced the moment when a mind suddenly perceives a new structure behind familiar phenomena. Why does this matter beyond the laboratory? Because the same tension between reason and intuition shapes every dimension of human existence. The individual navigating life faces the same challenge as the scientist confronting the universe. Experience alone does not generate meaning. Events occur, memories accumulate, impressions form. Yet the interpretation of those experiences requires an inner act of synthesis. Human beings constantly build narratives to explain their lives. Some narratives are cautious and defensive. Others are bold and imaginative. The difference between them often determines the boundaries of possibility a person is willing to explore. Here, the psychological dimension of Einstein's insight becomes visible. Most people fear imagination when it challenges established structures. Institutions prefer predictability. Traditions reward conformity. The mind itself often clings to familiar frameworks because uncertainty generates anxiety. But genuine discovery demands precisely the opposite movement. It demands intellectual risk. To imagine a new theory is to confront the possibility of failure. To question established knowledge is to invite resistance. Every revolutionary idea must first pass through the hostility of a world that believes it already understands itself. Einstein experienced this resistance repeatedly. His early ideas about relativity appeared almost absurd to many contemporaries. The notion that time could stretch or compress depending on motion seemed to violate common sense. But common sense is merely the accumulation of unexamined assumptions. The history of science repeatedly demonstrates that the universe is under no obligation to respect human intuition. Our everyday experience evolved within a narrow band of physical conditions. When investigation extends beyond that band, the underlying structure of reality begins to reveal unexpected patterns. Einstein understood this with extraordinary clarity. He trusted neither immediate perception nor inherited doctrine. Instead, he trusted the capacity of disciplined imagination to penetrate deeper layers of structure. Notice the existential courage required for such trust. Imagination can liberate the mind, but it can also destabilize it. When new conceptual frameworks appear, the familiar world begins to dissolve. The comfortable image of reality that once guided human life becomes provisional. This is precisely what occurred when relativity emerged. The stable clock of classical physics fractured. Time lost its universal rhythm. Space ceased to be an immutable stage. The cosmos revealed itself as something stranger and more dynamic than previously imagined. Yet this transformation did not produce chaos. It produced deeper coherence. The strange predictions of relativity eventually aligned with experimental observation. What imagination had first proposed reason and evidence gradually confirmed. The lesson becomes unmistakable. Scientific progress requires the courage to imagine realities that contradict immediate experience. And this courage has a psychological price. Human consciousness prefers certainty because certainty stabilizes identity. If the world behaves predictably, the self feels secure. But revolutionary insight demands that the thinker tolerate ambiguity long enough for new structures to emerge. This tolerance separates the conventional mind from the creative one. The conventional mind demands proof before belief. The creative mind allows provisional belief in order to discover proof. Between these two attitudes lies the entire drama of intellectual progress. Modern society often celebrates innovation while quietly fearing the instability that genuine innovation produces. New technologies appear everywhere, yet conceptual revolutions remain rare. The reason is simple. Tools can be developed incrementally, but new frameworks require dismantling old certainties. Einstein's life illustrates this tension vividly. His imagination did not operate in isolation from logic. Every intuitive leap was followed by relentless analysis. Equations were constructed to test the internal consistency of the vision. Only when the mathematical structure held together did the theory approach the threshold of empirical verification. This interplay between intuition and reason forms the beating heart of scientific discovery. A symbolic image clarifies the process. Imagine a thinker sitting alone with a blank sheet of paper. No experiment stands before him. No instrument gathers data. Yet, inside his mind, a question begins to grow. The visible world no longer feels complete. Something within the pattern of existing knowledge appears unresolved. The thinker begins to imagine possibilities. Perhaps time behaves differently than it appears. Perhaps space bends under the influence of mass. Perhaps the universe obeys principles that no one has yet articulated. These possibilities initially exist only as fragile ideas, but reason soon begins its work. The thinker tests the implications. Contradictions are exposed. Some visions collapse under logical scrutiny. Others survive. Gradually, a coherent structure emerges from the interplay between intuition and analysis. What began as imagination becomes theory. What began as speculation becomes explanation. And only after this conceptual architecture stands firmly does experimental evidence enter the stage. Observation confirms or refutes what imagination has proposed. The pattern repeats throughout the history of science. Every major revolution begins with a question that observation alone could not generate. This pattern reveals something profound about human cognition. The mind is not merely a recorder of events. It is an active generator of possibilities. And yet, imagination alone cannot claim authority over reality. Without the discipline of reason and the scrutiny of evidence, imagination easily descends into fantasy. True scientific creativity, therefore, inhabits a narrow path between two dangers. On one side lies rigid empiricism that refuses to imagine beyond existing data. On the other side lies uncontrolled speculation detached from reality. The genius of Einstein resided in his ability to walk precisely along this path. His thought experiments allowed him to explore possibilities beyond ordinary experience. His mathematical discipline ensured that those possibilities remained logically coherent. Through this balance, he transformed the foundations of physics. But even as these conceptual revolutions unfolded, another question began to emerge from the structure of his theories. If perception cannot be trusted completely, and imagination must guide reason toward deeper frameworks, then what about the most basic dimension of human experience? Time itself. For centuries, humanity believed time flowed identically for everyone. The present moment appeared universal, shared across the entire cosmos. Past events receded behind us. Future events waited ahead. But what if this comforting picture was another construction of perception? What if the flow of time itself depended on the motion of the observer? Time does not flow the way human intuition insists that it does. This statement strikes at one of the deepest illusions embedded in human consciousness. Every person feels time as a continuous river. The past disappears behind us. The future approaches from a distance. The present appears as a shared moment that sweeps across the universe like an invisible wave. But this image is not reality. It is a psychological construction. Long before the modern world fully grasped the consequences, Albert Einstein began dismantling the ancient belief in absolute time. His theory of relativity did not simply introduce a new equation into physics. It destroyed the assumption that the universe possesses a single universal clock. The shock of this idea cannot be overstated. For centuries, humanity inherited the framework established by Isaac Newton. In that framework, time flowed uniformly everywhere. Every observer shared the same cosmic rhythm. Events might occur at different locations, but the sequence of moments was universal. Newtonian time was absolute. Explanation reveals why this idea appeared so convincing. Human experience reinforces it every day. When two people sit together and watch a clock, its movement appears identical for both. Morning becomes afternoon. Afternoon becomes night. The rhythm of life unfolds with reassuring consistency. But everyday perception hides a deeper structure. Einstein recognized a disturbing possibility. What if time does not belong to the universe itself, but instead depends on the observer who measures it? This question begins with a philosophical claim. There is no universal present shared by the entire cosmos. Explanation follows immediately. In relativity, time becomes inseparable from motion. Observers who move differently through space experience time differently. Two events that appear simultaneous to one observer may occur at different moments for another. Evidence emerges through a simple thought experiment. Imagine two observers separated by great distance. A flash of light occurs exactly halfway between them. Because light travels at a constant speed, both observers will receive the signal at the same moment if they remain stationary relative to each other. But now imagine that one observer begins moving rapidly toward the flash, while the other moves away. The moving observer approaching the light will encounter it sooner. The other observer will receive it later. Each observer will construct a different account of when the event truly occurred. The notion of a shared present collapses. This conclusion reveals the first branch of Einstein's revolution. Simultaneity is not absolute. Events that appear to occur at the same moment for one observer may not be simultaneous for another. The second branch emerges from this insight. If simultaneity is relative, then the structure of time itself must depend on the observer's motion. The third branch completes the transformation. Time is not an independent cosmic river. It is a dimension woven together with space, forming a structure that changes according to the movement of the observer. This idea confronts human intuition with brutal force. Why does it feel so strange? Because our senses evolved within a narrow range of speeds and gravitational conditions. In daily life, the differences predicted by relativity are too small to notice. The illusion of universal time, therefore, persists. But the universe operates according to deeper laws than human comfort. When objects move at extremely high speeds, time begins to behave in ways that contradict ordinary experience. A clock carried by a rapidly moving observer will tick more slowly compared to a stationary one. Time itself stretches. This phenomenon is not philosophical speculation. It has been measured repeatedly in modern experiments. Atomic clocks placed aboard fast-moving aircraft return showing slight differences compared to clocks left on the ground. The implication is unavoidable. Time is elastic. Einstein's theory reveals that each observer carries a personal timeline shaped by motion and gravity. No single clock governs the entire cosmos. The universe contains countless overlapping temporal perspectives. This realization opens a profound existential question. If there is no universal present, what becomes of the moment we call now? Human consciousness treats the present as a shared reality. We imagine that all beings in the universe occupy the same slice of time. But relativity exposes the fragility of this assumption. Two distant observers may disagree about whether two events occur simultaneously. One observer may judge that event A occurs before event B. Another observer may conclude the opposite. Both perspectives can be correct. The comforting unity of time dissolves into a web of observer-dependent experiences. This discovery forces philosophy to confront a deeper problem. Human beings rely on temporal order to construct meaning. We organize memory according to past events. We imagine the future as something approaching us. Our identities unfold through narrative structures rooted in time. But if time itself is not universal, then the foundation of those narratives becomes uncertain. The mind resists this conclusion instinctively. Psychological stability depends on a stable sense of temporal flow. Without it, the world would feel disorienting. Yet physics insists on confronting the illusion. Einstein's insight reveals a brutal truth about human cognition. Our perception of time is not a direct encounter with reality. It is an interpretation shaped by biological constraints and limited experience. The universe itself may possess no preferred moment called now. Modern life continues to ignore this revelation. Even in the age of advanced technology, people speak casually about the present moment as if it were universally shared. Schedules, calendars, and global communication reinforce the impression of synchronized time. But beneath this practical coordination lies a deeper philosophical instability. In reality, every observer inhabits a slightly different temporal frame. This tension between practical convenience and physical truth illustrates the larger conflict between human intuition and scientific understanding. Einstein did not merely revise a detail within physics. He exposed the limits of the mental models through which humans interpret existence. Consider the psychological impact of this realization. If time depends on motion, then each individual occupies a unique path through the fabric of the universe. Two people standing side by side today will not share identical timelines if their motions differ even slightly. The difference may be minuscule, but it exists. Every life unfolds along its own temporal thread. This insight carries an unsettling implication. The universe is not synchronized around human experience. Our perception of shared moments is an approximation produced by the narrow conditions of everyday life. Beyond those conditions, the cosmos behaves differently. The deeper we investigate reality, the more our intuitive frameworks collapse. Yet the collapse of intuition does not lead to chaos. It reveals deeper coherence. Relativity replaces the illusion of absolute time with a precise mathematical structure connecting time and motion. This structure allows predictions of extraordinary accuracy. Satellites orbiting the Earth must account for relativistic effects to maintain the accuracy of global positioning systems. Without these corrections, modern navigation would fail. The universe therefore confirms Einstein's vision repeatedly. But the philosophical consequences extend far beyond technology. If time is relative, then the separation between past, present, and future may not be as rigid as human perception suggests. The idea of a universal moving present begins to lose meaning. Some thinkers began to consider a startling possibility. Perhaps the flow of time itself is not fundamental. Perhaps the universe contains all moments simultaneously, within a larger structure that human consciousness experiences sequentially. This possibility begins to shift our understanding of existence itself. Before Einstein, time appeared as a stage on which events occurred. After relativity, time becomes part of the structure in which those events exist. And once time becomes structural rather than flowing, the boundary between time and space begins to blur. What appears to us as separate dimensions may in fact belong to a single unified framework, a framework in which the geometry of the universe determines how motion, gravity, and time interact. And the moment this idea emerges, the universe begins to reveal a new architecture where space and time are no longer separate arenas, but elements of one deeper structure, waiting to be understood. Space and time are not separate arenas of existence. They are a single structure within which the entire drama of the universe unfolds. This claim shattered one of the oldest assumptions embedded in human thought. For centuries, people believed space was the stage and time was the clock. Objects moved through space while time flowed independently in the background. The universe appeared like a theater in which events occurred sequentially. But that picture was an illusion constructed by intuition. After revealing that time itself changes depending on motion, Albert Einstein pushed the inquiry further. If time varies with the observer and space determines motion, then the two cannot remain independent. They must belong to a deeper unity. This realization produced one of the most radical conceptual transformations in the history of science. Space and time fuse into a single continuum. Explanation begins with a simple but devastating observation. If two observers moving differently measure time differently, then distance and duration cannot be treated as separate quantities. The measurement of space affects the measurement of time, and the measurement of time affects the measurement of space. They form an inseparable pair. Evidence for this unity appeared clearly when Einstein's ideas were formalized mathematically by Hermann Minkowski. Minkowski proposed that reality should be understood not as 3 dimensions of space plus 1 dimension of time, but as a 4-dimensional structure where space and time intertwine. This structure became known as space-time. The philosophical consequences are enormous. In the old picture, the universe was a collection of objects moving through an empty container called space, while time ticked forward uniformly. In the new picture, space and time themselves become part of the architecture of reality. They form the fabric within which everything exists. This fabric is not rigid, it bends. The claim sounds almost poetic, but its meaning is brutally precise. Gravity is not a mysterious force pulling objects together across empty space. Gravity is the curvature of space-time itself. Explanation clarifies the structure. Massive objects such as stars and planets distort the geometry of space-time around them. When other objects move through this curved geometry, their paths change. What appears to us as gravitational attraction is simply the natural motion of bodies following the curved structure of space-time. Objects do not feel a force pulling them inward. They follow the geometry. Evidence for this strange idea emerged gradually through observation. Light passing near massive objects bends slightly. Time itself slows in stronger gravitational fields. Planets orbit stars not because of invisible forces acting at a distance, but because the structure of space-time around the star is curved. The universe behaves like a vast geometric architecture. This realization transforms our understanding of existence. Space is no longer empty. Time is no longer an independent flow. Together, they form a dynamic fabric that shapes the motion of everything within it. Einstein's insight, therefore, extends far beyond physics. It exposes a deeper philosophical truth about the nature of reality. Human perception divides the world into categories that appear obvious. Space here, time there, matter moving through both. But the deeper structure of the universe refuses to obey these convenient distinctions. Reality is unified where perception sees separation. This pattern appears again and again in the history of thought. Human intuition simplifies the world into manageable pieces. Scientific investigation repeatedly reveals that those pieces belong to larger wholes. The unity of space-time is one of the most powerful examples. Consider what this means for human understanding. If space-time is the fundamental structure of the universe, then every event that has ever occurred exists within this four-dimensional architecture. Past events occupy regions of space-time, just as physical locations occupy regions of space. In this view, an event is not simply something that happens and disappears. It becomes a point within the geometry of the universe. The philosophical implications are unsettling. Human consciousness experiences time sequentially. We feel ourselves moving from past to future through a fleeting present. But space-time suggests that the entire structure of events may already exist within the geometry of reality. Our experience of temporal flow may therefore be only a perspective. This idea forces the mind into uncomfortable territory. If space-time contains the full arrangement of events, then the distinction between past and future may not be fundamental. The universe might resemble an immense structure rather than a process unfolding moment by moment. Why does this possibility disturb human intuition? Because our identity is deeply tied to the sensation of movement through time. We experience ourselves as beings traveling from birth toward death. Our memories stretch behind us. Our hopes project ahead. But space-time invites a different image. Imagine reality as an enormous landscape containing every event. Within this landscape, the path of each individual life forms a trajectory. What we experience as the passage of time might simply be our consciousness moving along that trajectory. The world itself does not move. We do. Einstein himself resisted turning this interpretation into metaphysical doctrine, but the structure of his theory inevitably invites philosophical reflection. When space and time merge into a unified geometry, the entire cosmos begins to resemble an intricate architecture rather than a flowing story. This architecture is dynamic. Massive objects reshape it continuously. Stars bend the fabric around them. Galaxies curve the structure of space-time across enormous distances. The universe becomes a living geometry. Modern observation has revealed just how dramatic these distortions can be. When extremely massive objects collapse into dense states, the curvature of space-time becomes so intense that evil light cannot escape. These objects, later called black holes, demonstrate the extreme consequences of Einstein's insights. Gravity is geometry pushed to its limits. But beyond these spectacular phenomena lies a deeper existential resonance. If space-time is the foundation of reality, then every event is part of a vast interconnected structure. No event exists in isolation. Each moment depends on the geometry that surrounds it. The universe behaves less like a collection of independent objects and more like a single organism whose structure extends across both space and time. Human beings struggle to grasp this unity because everyday experience fragments reality. We perceive objects separately. We think of moments as isolated instances. But deeper investigation dissolves those boundaries. Even the simplest events involves the intersection of spatial position and temporal location within the larger geometry of space-time. Nothing exists outside that framework. This insight confronts the human mind with a humbling truth. The universe is not designed around human perception. Our senses evolved to navigate a narrow environment on a small planet. They present a simplified picture that allows survival but conceals deeper structures. Only through theoretical imagination and mathematical reasoning do those structures begin to emerge. Einstein, therefore, stands not only as a physicist, but as a philosopher of reality. His theories force humanity to reconsider the relationship between perception and truth. The visible world is only the surface. Beneath it lies a geometric architecture that governs the motion of stars, the bending of light, and the unfolding of cosmic history. Yet, even this extraordinary vision does not resolve every mystery. Because once space-time becomes the stage of the universe, another question inevitably rises from the shadows. If gravity emerges from the curvature of space-time, and if space-time itself forms the fundamental structure of reality, then what happens when the laws of nature appear to introduce randomness rather than order? Because while Einstein believed the universe possessed a deep rational structure, another theory was beginning to emerge that seemed to challenge that belief. A theory suggesting that at the smallest scales of existence, reality might not follow strict determinism at all. The universe, Einstein believed, must obey reason. This conviction was not merely scientific, it was philosophical. Beneath every equation and every theory lay a deeper faith that reality possesses an underlying order. The cosmos may appear chaotic on the surface, but beneath that surface there must exist a structure governed by precise laws. For Einstein, the universe was not a dice game. Yet during the same period that relativity reshaped our understanding of space-time, another revolution began to unfold inside physics. A new framework emerged that described nature at its smallest scales. And unlike relativity, this new theory did not promise certainty. It introduced probability. The theory became known as quantum mechanics. This development created one of the most dramatic intellectual confrontations in the history of science. On one side stood the deterministic vision that Einstein believed defined the rational structure of the universe. On the other side stood a new generation of physicists who argued that uncertainty was woven into the fabric of reality itself. Among them were figures such as Niels Bohr and Werner Heisenberg. Their message was unsettling. At the smallest scales of existence, events do not follow strict causal chains. Instead, they unfold according to probabilities. The behavior of particles cannot always be predicted with certainty. Only the likelihood of different outcomes can be calculated. This claim shook the philosophical foundations of science. For centuries, physics had pursued the dream of determinism. If the state of a system were known precisely at one moment, then the laws of nature would allow its future to be calculated exactly. This vision reached its most elegant form in the classical mechanics of Isaac Newton. The universe appeared as a perfectly ordered machine. Every motion had a cause. Every event followed logically from previous conditions. The future was simply the unfolding of the present, according to universal laws. Einstein inherited this intellectual tradition and expanded it with extraordinary brilliance. Relativity revealed that space and time form a unified structure. Gravity emerges from geometry. The cosmos behaves according to elegant mathematical principles. But quantum mechanics introduced a disturbing element: Londonness. The tension can be expressed as a philosophical claim. Reality is either fundamentally ordered or fundamentally probabilistic. Explanation reveals the depth of the problem. Quantum theory describes particles not as objects with definite positions and velocities, but as probability distributions. Before measurement occurs, the theory does not specify exactly where a particle is. It describes only the range of possibilities. When observation occurs, one possibility becomes actual. Evidence for this strange behavior appears repeatedly in experiments. Particles behave like waves when unobserved, and like localized objects when measured. Their properties remain uncertain until interaction forces a specific outcome. This phenomenon forced physicists to reconsider the meaning of reality itself. Einstein found the implications deeply troubling. To him, the idea that nature fundamentally relies on randomness felt incomplete. Probability might reflect our ignorance, but it should not represent the ultimate structure of the universe. Somewhere beneath the apparent uncertainty, there must exist hidden laws governing events with perfect precision. His disagreement with quantum theory therefore became philosophical as much as scientific. Einstein famously expressed his objection with a sentence that has echoed through intellectual history: "God does not play dice with the universe." This statement was not a religious declaration. It was an expression of metaphysical conviction. The universe must possess rational order. But proponents of quantum mechanics responded differently. They argued that Einstein's insistence on determinism reflected human intuition rather than physical evidence. Experiments consistently supported the probabilistic predictions of quantum theory. Nature seemed comfortable with uncertainty. This conflict produced one of the most fascinating debates ever recorded in science. Einstein challenged the quantum framework repeatedly, proposing thought experiments designed to expose contradictions. One of the most famous involved what later became known as the EPR paradox, developed with Boris Podolsky and Nathan Rosen. The argument attempted to show that quantum mechanics could not be a complete description of reality. According to the reasoning, if quantum predictions were correct, then particles separated by enormous distances could influence each other instantaneously. Such influence would violate the principle that no signal travels faster than light, a principle central to relativity. Einstein found this possibility unacceptable. He described it as a strange action at a distance. For Einstein, the idea threatened the logical coherence of the universe. A rational cosmos should not allow instantaneous connections across space without a clear causal mechanism. Yet the story did not end with Einstein's objection. Decades later, experiments began to test the predictions associated with quantum entanglement. Astonishingly, the results supported the quantum perspective. Particles that interact and then separate appear to remain connected in ways that defy classical intuition. Measurement of one particle can instantly determine the state of another, regardless of the distance between them. The implications are staggering. Reality may contain correlations that transcend ordinary spatial separation. The universe might be more interconnected than classical physics ever imagined. For many physicists, these results confirmed the probabilistic interpretation of quantum mechanics. Uncertainty is not merely ignorance, it may be fundamental. Yet the philosophical discomfort remains. Human reason longs for causal clarity. We instinctively search for mechanisms that explain why events occur. Randomness feels like an admission of defeat. Einstein's resistance, therefore, reveals something essential about the psychology of knowledge. The human mind seeks order because order provides meaning. If the universe operates according to precise laws, then reality becomes intelligible. If events occur randomly, understanding appears fragile. But perhaps this tension reflects a deeper limitation within human cognition. Our minds evolved to interpret patterns within environments where cause and effect are visible. The microscopic world may operate according to principles that transcend those intuitive expectations. Quantum mechanics confronts us with the possibility that reality contains layers inaccessible to classical reasoning. Yet even here, the story remains unfinished. Einstein never accepted the finality of the quantum interpretation. He believed the theory described statistical patterns without revealing the deeper structure beneath them. Somewhere within the universe, hidden variables might still determine outcomes with absolute precision. His search for deeper unity never ended. This persistence reflects a powerful philosophical attitude. Even when confronted with evidence suggesting randomness, Einstein continued to believe that a deeper order must exist. This belief was not stubbornness alone. It was a commitment to the idea that the universe is ultimately intelligible. Modern physics still wrestles with this question. Some researchers embrace the probabilistic interpretation fully. Others search for deeper frameworks that might reconcile quantum mechanics with determinism. The debate continues because the underlying philosophical problem remains unresolved. Is the universe fundamentally governed by necessity or by chance? This question reaches far beyond physics. Human life itself unfolds within uncertainty. We plan carefully, yet outcomes remain unpredictable. We search for meaning in events that often appear random. The tension between determinism and probability echoes within the structure of our own existence. Einstein's resistance to randomness therefore carries existential weight. It represents the refusal to accept a universe that cannot ultimately be understood. Yet quantum mechanics continues to challenge that hope. If reality contains irreducible uncertainty, then knowledge may always remain incomplete. The universe might not be a perfectly predictable machine, but a dynamic field of possibilities. And once this idea enters the conversation, another question inevitably emerges from its shadow. If events become definite only when observed, then what role does the observer play in the structure of reality itself? Reality must exist whether or not we observe it. This conviction stood at the center of Einstein's philosophical rebellion against quantum mechanics. It was not a technical disagreement about equations. It was a confrontation over the nature of existence itself. Does the world possess objective structure independent of the human mind? Or does observation play a role in bringing reality into form? For centuries, philosophy assumed the first answer. Mountains exist whether anyone looks at them. Stars burn whether anyone sees them. The universe unfolds according to laws that operate independently of human awareness. Einstein shared this belief with unwavering clarity, but the emerging framework of quantum theory began to whisper a different possibility. At the microscopic level, the act of measurement appears to influence the state of physical systems. Before observation, particles are described not as definite objects, but as probability distributions. Only when measured do they assume specific properties. This strange feature of quantum mechanics forced scientists to confront a deeply unsettling question. Does reality exist in a definite state before it is observed? For Einstein, the answer had to be yes. He believed the universe possessed an objective structure independent of observers. Physical systems must have real properties, even when no one measures them. Otherwise, science would lose its foundation. If reality depends on observation, then the world becomes entangled with consciousness in ways that defy traditional understanding. Einstein refused to accept such ambiguity. Yet many of his contemporaries, especially Niels Bohr, interpreted quantum mechanics differently. Bohr argued that physics should not attempt to describe reality as it exists independently of measurement. Instead, it should focus on what can be observed and predicted through experiments. In this interpretation, the properties of quantum systems become meaningful only when measurement occurs. This view did not necessarily claim that consciousness creates reality, but it suggested that the act of observation plays a fundamental role in determining physical outcomes. The tension between these positions reshaped the philosophy of science. The argument begins with a philosophical claim. Reality must either exist independently of observation or depend in some way on the act of measurement. Explanation reveals the core difficulty. Quantum mechanics describes systems using mathematical expressions that represent multiple possible states simultaneously. Before measurement, a particle may exist in a superposition of possibilities. Only when interaction occurs does the system appear to collapse into a single outcome. Evidence emerges through experiments that repeatedly confirm this strange behavior. When particles pass through certain experimental arrangements, they produce interference patterns that suggest wave-like behavior. Yet, when detectors attempt to determine their path, the pattern disappears, and the particles behave like localized objects. The act of measurement alters the phenomenon. This result unsettled Einstein, because it appeared to place the observer in an unusual position within the structure of reality. If physical systems remain indefinite until measured, then the boundary between observer and observed becomes philosophically significant. Einstein believed such a boundary must be artificial. The universe existed long before human beings appeared. Stars formed billions of years before observers existed to measure them. If observation were necessary for reality to become definite, then the cosmos would have remained indeterminate until conscious beings emerged. This idea felt absurd to Einstein. His resistance culminated in the argument known as the EPR paradox, developed with Boris Podolsky and Nathan Rosen. Their reasoning attempted to show that quantum mechanics could not provide a complete description of physical reality. If two particles interact and then separate, measuring one particle instantly determines the state of the other. According to Einstein, this implied either instantaneous influence across space or incomplete knowledge within the theory. Both possibilities troubled him. Einstein preferred the second interpretation. Quantum mechanics must be incomplete. Hidden variables might exist beneath the statistical framework, variables that determine outcomes with precision, even if current theory cannot describe them. The debate remained unresolved during Einstein's lifetime. Yet decades later, experimental investigations began to test the deeper implications of entanglement. These experiments revealed that correlations between entangled particles exceed what classical hidden variable theories can explain. The results suggest that the universe contains connections more subtle than classical physics predicted. Particles separated by great distances behave as if they share information instantaneously. The structure of reality may therefore be deeply non-local. This discovery does not necessarily mean that observers create reality, but it does suggest that the act of measurement cannot be ignored when describing physical phenomena at quantum scales. The boundary between observer and system becomes blurred. This insight forces philosophy into unfamiliar territory. Traditional realism assumes that objects possess definite properties regardless of observation. Quantum mechanics challenges that assumption by showing that certain properties emerge only through interaction. Reality may not be a static collection of independent objects. Instead, it may be a network of relationships. Human beings find this idea difficult to accept because perception encourages the opposite belief. We see objects with clear boundaries. We imagine a world composed of separate entities interacting through forces. But quantum phenomena hint at a deeper, interconnected structure where separations are less absolute than they appear. The implications reach beyond physics. If observation plays a role in shaping measurable outcomes, then knowledge itself becomes a participatory process. The observer is not entirely detached from the system being studied. Yet this participation should not be misunderstood as subjective creation of reality. Quantum theory does not imply that human thoughts generate physical events. Instead, it reveals that the act of interaction between measuring apparatus and system determines which possibilities become actual. Reality emerges through interaction. Einstein struggled with this idea because it appeared to compromise the objective independence of the universe. He feared that abandoning realism would lead science into philosophical confusion. But even those who supported the quantum interpretation recognized the depth of the mystery. The role of observation remains one of the most debated issues in modern physics. Some interpretations attempt to preserve realism by proposing multiple parallel outcomes existing simultaneously. Others suggest that the wave function represents knowledge rather than physical reality. Still others explore the possibility that reality emerges through relational interactions between systems. The debate continues because quantum mechanics reveals a universe far stranger than classical intuition allowed. Einstein's resistance, therefore, reflects more than scientific disagreement. It represents a defense of a worldview in which the universe possesses stable structure independent of human inquiry. Yet quantum theory refuses to provide an easy answer. The more deeply physicists investigate the microscopic world, the more the boundary between observer and system dissolves. Measurement becomes part of the phenomenon rather than an external act. This realization forces philosophy to reconsider the nature of objectivity itself. Perhaps objectivity does not mean complete independence from observers. Perhaps it means that the laws governing interactions remain consistent regardless of who performs the observation. In this sense, the universe still obeys universal principles, but the manifestation of specific outcomes depends on interactions occurring within the system. Reality becomes relational. Human beings may not create the universe through observation, but they participate in the network of interactions through which physical states become defined. Einstein never accepted this perspective fully. His intuition demanded a deeper, deterministic order beneath the probabilistic surface of quantum theory. Yet even his opposition played a crucial role in shaping modern physics. By challenging the quantum interpretation repeatedly, Einstein forced physicists to clarify their assumptions and test their theories with increasing precision. His skepticism sharpened the debate, and the debate itself revealed a profound truth about the human search for knowledge. Science does not advance through agreement alone. It advances through tension between competing visions of reality. Each challenge exposes hidden assumptions. Each disagreement forces deeper investigation. Einstein's insistence on realism kept alive the question of whether the universe ultimately possesses an objective structure independent of observers. Quantum mechanics kept alive the possibility that reality reveals itself only through interaction. Between these perspectives lies one of the deepest philosophical puzzles in modern thought. And as the implications of quantum theory continued to unfold, Einstein's own reflections began to move toward a different dimension of inquiry. If the universe possesses hidden order beneath its apparent complexity, then perhaps the deepest question is not whether reality exists independently of observation, but whether the structure of that reality reflects a deeper harmony within nature itself. A harmony that some thinkers might even dare to describe using a word that science rarely speaks aloud. God, for Einstein, was not a being. God was order. This statement strips away centuries of misunderstanding. When many people hear the name of Albert Einstein, they imagine a scientist flirting with religion or a mystic speaking about divine forces. But the reality is far more severe and far more philosophical. Einstein did not believe in a personal deity who listens, judges, or intervenes in human affairs. What he believed in was something colder, deeper, and infinitely more unsettling. He believed that the universe possesses a rational structure so profound that encountering it evokes something resembling religious awe. To understand this idea, we must first strip away the ordinary meaning of the word God. For Einstein, the word did not refer to a supernatural ruler. It referred to the hidden harmony of nature itself. The universe operates according to principles that the human mind can gradually uncover. Behind the apparent chaos of phenomena lies a mathematical coherence. This conviction places Einstein within a philosophical tradition much older than modern physics. Centuries earlier, the philosopher Baruch Spinoza had proposed a radical idea. God is not a separate creator standing outside the universe. God is identical with the structure of reality itself. The divine is not a person, but the totality of nature and the laws governing it. Einstein admired this view deeply. The famous phrase often attributed to him clarifies the connection. When asked about his religious beliefs, Einstein replied that he believed in Spinoza's God, the God revealed in the lawful harmony of what exists. This statement contains a philosophical bomb. It declares that the universe itself is sacred, not because it serves human purposes, but because its structure expresses a profound, rational order. The argument unfolds in three movements. The first movement begins with a claim. The universe displays astonishing coherence. The same physical laws govern the motion of galaxies and the vibration of atoms. Mathematical relationships discovered by human reason accurately describe phenomena across unimaginable scales. Explanation deepens the point. This coherence is not trivial. The cosmos could have been chaotic and unintelligible. Instead, it reveals patterns that can be expressed through elegant equations. The success of physics therefore suggests that the structure of the universe resonates with the structure of human thought. Evidence emerges from the history of scientific discovery itself. The equations of relativity predicted the bending of light by gravity before it was observed. Quantum theory predicted phenomena that later appeared in experiments. Mathematical reasoning repeatedly reveals aspects of reality before observation confirms them. The universe behaves as if it were written in a language that human minds can learn. This realization produced in Einstein a sense of intellectual reverence, not worship in the traditional religious sense, but something closer to awe before the rational beauty of nature. The second movement of the argument exposes a common misunderstanding. Many people imagine that science destroys spiritual experience. But for Einstein, the opposite was true. The deeper science penetrated into the structure of reality, the more mysterious and magnificent the universe appeared. Ignorance breeds arrogance. Knowledge breeds humility. The scientist who glimpses the underlying harmony of nature confronts a reality far greater than individual existence. The cosmos operates according to principles that existed long before humanity and will continue long after human civilization disappears. In that confrontation, the ego dissolves. Einstein often spoke of what he called the cosmic religious feeling. This feeling does not depend on rituals or doctrines. It arises when the human mind recognizes that it is confronting a universe whose rational order surpasses individual understanding. The scientist becomes a witness to the architecture of reality. The third movement of the argument reveals the ethical dimension of this vision. If the universe possesses deep rational structure, then the search for knowledge becomes more than technical activity. It becomes a philosophical calling. The pursuit of truth is not merely practical. It expresses the human desire to align thought with the fundamental order of nature. Science becomes contemplation. Yet this vision contains no comfort. Einstein's cosmic perspective offers no promise of personal salvation, no assurance that the universe cares about human suffering. The rational structure of nature does not exist to serve human desires. Stars explode, galaxies collide, species vanish. The cosmos remains indifferent. But precisely within that indifference lies its profound beauty. The universe does not flatter the human ego. It reveals a structure that transcends human purposes entirely. This realization forces humanity to confront its true position. We are not the center of creation. We are temporary observers within an immense and ancient system. Our significance lies not in cosmic importance, but in our capacity to understand. The ability to glimpse the order of the universe becomes the most extraordinary privilege of human consciousness. Einstein therefore rejected both dogmatic religion and shallow materialism. Dogmatic religion reduces the universe to a moral theater governed by divine intention. Shallow materialism reduces reality to mechanical processes devoid of meaning. Einstein's vision stands somewhere deeper. The universe is rational. The universe is intelligible. And the act of understanding it evokes a feeling of reverence that resembles spirituality without invoking supernatural authority. This position confuses people because it refuses easy categories. Einstein was neither a traditional believer nor a strict atheist. He occupied a philosophical space where scientific insight and existential wonder intersect. To him, the greatest mystery was not the existence of God in a personal sense. The greatest mystery was that the universe is comprehensible at all. Why should mathematical structures invented by human minds correspond so precisely to the behavior of nature? Why should abstract reasoning reveal truths about distant galaxies or microscopic particles? Einstein described this as the most incomprehensible fact about the universe, that it is comprehensible. This paradox deepens the philosophical tension running through his work. On one side stands the belief that the cosmos follows rational laws. On the other side stands the recognition that human understanding of those laws remains incomplete. Between these two poles lies the endless pursuit of science. Modern humanity often forgets this deeper dimension of scientific inquiry. Technology dominates public imagination. Scientific discoveries are celebrated for their practical applications. Yet Einstein insisted that the true motivation of science is something far more profound. It is the desire to penetrate the hidden order of reality. This desire does not emerge from utility. It emerges from existential curiosity. Human beings are driven to ask questions that offer no immediate survival advantage. We want to know why the universe exists, why it behaves as it does, why mathematical patterns appear throughout nature. These questions define the philosophical core of science. Einstein's reverence for the rational structure of nature therefore carries an implicit challenge to modern culture. A civilization obsessed with consumption and distraction risks losing contact with the deeper mystery of existence. To study the universe is to confront something immense and humbling, and that confrontation transforms the way we see ourselves. When the mind recognizes that the laws governing distant galaxies also govern the atoms within our own bodies, the boundary between the individual and the cosmos begins to blur. Human existence becomes a brief expression of the same physical principles shaping the entire universe. We are fragments of cosmic order becoming conscious of itself. This realization produces a strange mixture of humility and wonder. Our lives are insignificant compared with the scale of the universe, yet our capacity to understand that universe is astonishing. Einstein's vision, therefore, does not offer religious comfort, but it does offer intellectual dignity. The search for truth becomes the highest expression of human freedom. Yet even this vision leaves one profound puzzle unresolved. If the universe possesses deep rational harmony, and if the structure of space-time contains the architecture of events, then the nature of time itself demands further examination. Because relativity had already suggested something deeply unsettling. The division between past, present, and future may not be fundamental at all. And if that is true, then the universe may not be unfolding moment by moment the way human consciousness experiences it. Instead, reality might resemble something far stranger, a vast structure in which all moments exist together, waiting to be understood. The past and the future may exist together. This idea strikes the human mind like a hammer. Everything in ordinary experience tells us that time moves. Yesterday is gone. Tomorrow has not yet arrived. The present feels like a narrow bridge between two abysses. We walk across it without ever stopping. Yet the deeper structure of relativity suggests something profoundly different. Time may not flow at all. This claim emerges naturally from the theories developed by Albert Einstein. Once space and time merge into a single structure known as space-time, the traditional picture of a moving present begins to collapse. In the geometry of space-time, events do not appear as fleeting moments that come into existence and vanish. They appear as fixed points within a larger four-dimensional structure. The universe begins to resemble an immense landscape rather than a river. Explanation reveals the philosophical force of this idea. If space-time contains all events, then past, present, and future occupy different regions of the same structure. Just as every location exists simultaneously within space, every moment may exist simultaneously within space-time. The human mind does not experience this structure directly. Instead, consciousness moves along a path inside space-time. That path is called a world line. Each observer traces a unique trajectory through the geometry of the universe. Along that trajectory, events appear sequential. Memory records what lies behind. Expectation imagines what lies ahead. But the structure itself may already contain every point. Evidence for this perspective appears implicitly within relativity. Different observers moving at different speeds disagree about which events are simultaneous. What one observer calls the present may belong to the past or future for another. If simultaneity is relative, then the notion of a universal present loses meaning. There is no single cosmic moment shared by all observers. Instead, there exists a vast network of events connected through space-time geometry. Each observer slices this structure differently, according to motion and perspective. The present becomes a viewpoint rather than a universal fact. This insight gave rise to what later philosophers called the block universe. In this view, the universe is not a process unfolding step by step, but a complete structure containing every event that has ever occurred or will occur. Imagine a book. All pages of the book exist simultaneously. The reader experiences the story sequentially only because they move through the pages one at a time. The narrative unfolds for the reader, but the entire structure of the story already exists within the book. Space-time may operate in a similar way. Human consciousness experiences time as a moving present because awareness travels along a path within the larger structure. But from the perspective of the universe itself, there may be no movement at all. Every moment simply exists. The claim produces deep psychological resistance. Human identity depends on the sensation of becoming. We feel ourselves moving from childhood toward old age. We imagine the future as open possibility. We mourn the past as something lost. The block universe challenges this entire emotional framework. If all moments exist within space-time, then the past has not vanished. It occupies another region of the structure. The future is not empty. It may already exist as part of the same cosmic architecture. Our experience of temporal flow may therefore be a feature of consciousness rather than a property of reality itself. Einstein himself hinted at this interpretation in a letter written after the death of a close friend. He remarked that for those who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. The sentence reveals the existential depth of his vision. Time, which governs every human emotion, may be less fundamental than we believe. Why does consciousness experience time as flowing if space-time is static? The answer remains mysterious. One possibility is that the brain constructs the sensation of temporal movement in order to organize memory and anticipation. Biological organisms require a sense of sequence to survive. Events must be ordered so that cause leads to effect within perception. The brain therefore converts the geometric structure of space-time into the psychological experience of temporal passage. Another possibility suggests that consciousness itself might correspond to movement along world lines within space-time. Each moment of awareness corresponds to a different point along the trajectory of the brain's physical state. The flow of time becomes the flow of consciousness. Regardless of the mechanism, the philosophical implications remain staggering.
If the block universe model captures something real about the structure of space-time, then the future may be as fixed as the past. Events that have not yet entered human awareness might already occupy locations within the geometry of reality. Human freedom suddenly becomes difficult to define. If tomorrow already exists somewhere in space-time, then in what sense can it be changed? This question reveals the tension between physics and human experience. Relativity describes the structure of events, but says little about the nature of choice. Our subjective sense of freedom arises from the fact that we cannot see the future portion of our world line. From within the present moment, the future appears open, but the geometry of space-time may already contain the entire path. This possibility does not necessarily eliminate freedom. Some philosophers argue that our decisions are part of the structure itself. The choices we make are the mechanisms through which future events become part of our world line. Freedom exists within the block rather than outside it. The universe contains the outcome of decisions, but those decisions still arise from the internal processes of conscious beings. Yet the block universe perspective forces a more radical reflection. Human life may not be a journey through time in the way we imagine. Instead, it may be a path embedded within a larger structure that transcends the temporal divisions of past and future. Every moment of existence becomes equally real within the architecture of space-time. This vision produces an unexpected form of existential clarity. Moments we consider lost may still exist within the structure of the universe. The laughter of childhood, the silence of forgotten afternoons, the quiet conversations that shaped our lives, all remain part of space-time's geometry. They have not vanished. They occupy other coordinates in the cosmic structure. From the perspective of consciousness, these moments lie behind us. From the perspective of space-time, they remain woven into the fabric of reality. Einstein's reflections suggest that the tragedy of time may be partly an illusion produced by human perception. Yet even within this grand structure, another puzzle emerges. Relativity describes space-time as a continuous geometric framework shaped by mass and energy. Quantum mechanics, however, introduces uncertainty and probability at the smallest scales. The two theories describe reality with extraordinary accuracy within their respective domains, but they do not yet fully agree. The geometry of space-time appears smooth and deterministic. The quantum world appears probabilistic and fragmented. Somewhere beneath these two descriptions, the universe may hide a deeper unity. Einstein spent the later years of his life searching for that unity. He believed that the forces governing nature must ultimately arise from a single coherent framework. Gravity, electromagnetism, and perhaps even the mysterious quantum forces might belong to one underlying structure. The search became known as the quest for a unified field. It was not merely a technical problem.
It was the continuation of a philosophical conviction that had guided Einstein from the beginning. The universe must possess deep coherence, and if that coherence exists, then the geometry of space-time and the strange probabilities of quantum theory may eventually reveal themselves as different expressions of the same hidden order. Somewhere beneath the visible equations, the cosmos may still be waiting to reveal its most profound unity. The universe must ultimately be one. This was not merely a scientific ambition for Albert Einstein. It was a philosophical necessity. If the cosmos truly possesses rational structure, then its laws cannot remain fragmented forever. Separate forces governing different phenomena would represent an incomplete understanding. Beneath the apparent diversity of physical interactions, there must exist a deeper unity. Einstein believed this with unyielding intensity. Throughout the early triumphs of relativity, he had already demonstrated that reality hides profound simplicity beneath complexity. Space and time, once treated as independent elements of existence, revealed themselves as a single continuum. Gravity, once imagined as a mysterious force acting across distance, emerged as geometry. What appeared separate became unified. From this success, Einstein drew a powerful conclusion. The universe favors elegance. Its deepest principles are not arbitrary collections of rules, but expressions of a coherent structure. The search for unity, therefore, became the final mission of his intellectual life. Explanation reveals why this quest mattered so deeply. Physics in the early 20th century described nature through several fundamental forces. Gravity governed the motion of planets and galaxies. Electromagnetism governed light and the behavior of charged particles. Later discoveries revealed additional forces responsible for processes within atomic nuclei. Each force operated according to different mathematical laws. To many scientists, this diversity appeared natural. The universe might simply contain several independent interactions. But Einstein saw fragmentation where others saw completion. For him, the existence of separate forces signaled unfinished knowledge. If space-time could unify space and time, perhaps a deeper framework could unify the forces themselves. The dream took shape as the search for a unified field theory. The claim driving this effort was simple but radical. All physical forces may be different expressions of a single underlying structure. Explanation clarifies the idea. Instead of treating gravity and electromagnetism as distinct interactions, one might imagine that both emerge from deeper geometric properties of space-time. In such a theory, the apparent diversity of forces would dissolve into variations of one fundamental field. Evidence encouraging this possibility already existed in the success of relativity. Einstein's equations had transformed gravity from a force into curvature within space-time geometry. If geometry could generate gravity, perhaps other forces could arise from geometry as well. Reality might therefore possess a single mathematical architecture from which every physical phenomenon emerges. Einstein spent decades pursuing this vision, yet the path proved far more difficult than his earlier triumphs. The mathematical structures capable of describing unified interactions remained elusive. Meanwhile, quantum mechanics advanced rapidly, producing extraordinarily accurate predictions about atomic and subatomic phenomena. But Einstein remained dissatisfied. Quantum theory described probabilities rather than deterministic structures. It treated forces as interactions between particles, mediated by uncertain processes. For Einstein, this framework lacked the conceptual clarity he believed fundamental physics required. He searched instead for equations expressing pure geometric unity. Many younger physicists gradually turned away from his approach. Quantum theory generated successful experimental predictions, while Einstein's unified field program produced no decisive breakthroughs. To some observers, it appeared that the great architect of relativity had become isolated within his own philosophical vision. Yet the deeper significance of Einstein's search lies not in its immediate success, but in the question it embodied. Is the universe ultimately coherent? The desire for unity reflects a profound feature of human reason. When confronted with complexity, the mind seeks patterns that reduce multiplicity to simplicity. Science advances precisely through this reduction. Diverse phenomena become understandable when they are revealed as consequences of common principles. Newton unified the motion of falling apples with the motion of planets. Maxwell unified electricity and magnetism into a single electromagnetic field. Einstein unified space and time and reinterpreted gravity as geometry. Each step revealed hidden coherence. Einstein believed that the pattern must continue. Nature should not end with fragmented laws. The philosophical argument unfolds in three stages. First comes the claim that the universe exhibits extraordinary internal consistency. The same mathematical structures often appear in widely different physical contexts. This recurrence suggests that deeper connections remain undiscovered. Second comes the explanation that fragmented theories typically signal incomplete understanding. When separate laws describe related phenomena, scientists search for frameworks that integrate them. Third comes the conclusion that ultimate understanding requires discovering the fundamental structure from which all physical interactions arise. Unity becomes the horizon toward which scientific thought moves. Yet the modern development of physics introduced a complication Einstein did not fully embrace. Quantum field theory eventually unified electromagnetism with certain nuclear forces through sophisticated mathematical frameworks. Later research revealed that forces once considered distinct might indeed be aspects of deeper symmetries. Ironically, the direction of modern physics began to echo Einstein's intuition. Grand unified theories attempt to describe several forces through a single mathematical structure. String theory proposes that all particles and interactions arise from vibrations of fundamental entities embedded within higher dimensional space. The language has changed, but the ambition remains familiar. Scientists continue searching for a theory of everything. This phrase captures the enduring influence of Einstein's vision. The idea that the cosmos possesses a single underlying order continues to drive theoretical research decades after his death. Yet the quest also exposes a deeper philosophical tension. The more unified our theories become, the further they move from ordinary human intuition. Higher dimensional geometries, quantum fields, and abstract symmetries stretch the limits of imagination. The ultimate structure of the universe may be mathematically elegant, but conceptually alien to everyday experience. Understanding, therefore, demands intellectual humility. Einstein himself embodied this humility despite his reputation for certainty. He often emphasized that the human mind grasps only fragments of cosmic order. Our theories approximate reality, but never capture it completely. The search for unity may therefore be endless. But even if the final theory remains beyond reach, The pursuit itself transforms our relationship with the universe, because every attempt to unify nature forces us to look beyond appearances. The visible diversity of phenomena hides deeper patterns. Stars, atoms, light, gravity, and perhaps even consciousness may belong to a single unfolding structure. Human beings, composed of the same physical laws that govern galaxies, become participants in that unity. The philosophical consequence is profound. We often imagine ourselves as isolated individuals, struggling within an indifferent cosmos. Yet the scientific search for unity reveals that every human life is woven into the same fabric that shapes the entire universe. The atoms within our bodies obey the same principles that govern distant stars. The laws guiding our biological processes emerge from the same fields that structure space-time itself. We are expressions of cosmic order, becoming aware of its own existence. Einstein's lifelong search for unity, therefore, carries existential significance. It suggests that the human drive to understand the universe is not accidental. Consciousness itself may represent a continuation of the universe's own tendency toward coherence. Through thought, the cosmos examines itself. Yet even this vision does not resolve the final question that haunted Einstein's reflections. If the universe possesses deep unity, if its laws form a coherent structure accessible to reason, then another mystery emerges with quiet persistence. Why should the human mind be capable of grasping that structure at all? Why should the abstract patterns discovered by thought correspond so precisely to the architecture of reality? The answer to this question leads directly to the philosophical conviction that guided Einstein from the beginning: the belief that the universe must be intelligible. The universe must be intelligible, or the human search for truth would be meaningless. This conviction stood at the deepest core of the philosophy of Albert Einstein. Long after the triumphs of relativity, long after the debates with quantum mechanics, long after decades spent chasing the dream of a unified field, one belief continued to guide his thinking with quiet but relentless force. Reality must be capable of being understood. Not completely, not perfectly, but sufficiently that the human mind can grasp its structure through reason. This belief was never proven. It could not be proven. It was an act of philosophical courage. Einstein understood this clearly. The success of science does not logically guarantee that the universe is rationally accessible. The cosmos could have been chaotic beyond comprehension. Its laws might have been too complex for any mind to penetrate. The patterns of nature might have refused all mathematical description. Yet the opposite appears to be true. Time and again, the universe reveals hidden simplicity beneath apparent complexity. Mathematical ideas conceived within human imagination suddenly illuminate distant stars, atomic interactions, and the geometry of space-time. This is the miracle that haunted Einstein. Explanation reveals the depth of the mystery. Human beings evolve through biological processes aimed at survival, not cosmic understanding. Our senses detect only narrow ranges of light and sound. Our brains develop to recognize predators, find food, and navigate landscapes. Nothing in evolution required that the human mind comprehend the structure of the universe. And yet it does. Equations written on paper predict phenomena billions of light years away. Abstract reasoning reveals laws governing events long before instruments confirmed them. The same mathematics describing falling objects also describes the motion of galaxies. The universe appears strangely cooperative with human thought. Evidence of this cooperation fills the history of science. The laws discovered by Isaac Newton describe both apples falling from trees and planets orbiting the sun. The equations of relativity predicted the bending of light and the slowing of time in strong gravitational fields before experiments confirmed them. Quantum theory described atomic behavior that no human eye had ever witnessed. In each case, the mind reached beyond experience and found reality waiting. This phenomenon cannot be dismissed as coincidence. Einstein believed it reveals something fundamental about the relationship between thought and nature. The structure of the human intellect, at least in part, mirrors the structure of the universe itself. This claim does not suggest that humans are central to the cosmos. On the contrary, Einstein consistently rejected any idea placing humanity at the center of creation. The claim is more subtle. Human reason may be a small reflection of the same order that governs the universe. If the cosmos is built upon rational principles, then minds capable of recognizing patterns might gradually uncover those principles. Our ability to understand the universe would therefore arise not from human superiority, but from participation in the same logical structure. We think with the universe because we are made of it. This idea transforms the meaning of scientific inquiry. Science becomes more than a collection of techniques. It becomes a philosophical dialogue between human thought and cosmic order. Each discovery represents a moment in which the structure of reality becomes visible to the structure of the mind. The scientist does not impose meaning on nature. The scientist discovers meaning already embedded within it. Yet Einstein never treated this harmony as guaranteed. His reflections repeatedly returned to a difficult truth. The intelligibility of the universe is not something we can take for granted. It is something that continually astonishes. He once remarked that the most incomprehensible thing about the universe is that it is comprehensible. This sentence carries immense philosophical weight. The universe could have been silent to human inquiry. Instead, it answers questions posed by mathematics and logic. The dialogue between mind and cosmos continues across centuries. But the dialogue remains incomplete. Every discovery opens new mysteries. Relativity revealed the geometry of space-time, yet the origin of space-time itself remains unknown. Quantum mechanics describes microscopic phenomena with extraordinary accuracy, yet its interpretation continues to provoke debate. The search for a unified theory continues to challenge the limits of imagination. Knowledge expands, but the horizon expands with it. Einstein understood this paradox with clarity. The progress of science does not lead toward final certainty. It leads toward deeper questions. Each layer of understanding reveals another beneath it. The philosophical lesson is severe. Human beings crave ultimate answers. We long for a final explanation that closes the circle of inquiry. But the structure of knowledge may never provide such closure. Understanding advances through approximation, refinement, and revision. Truth appears gradually, never completely. For Einstein, this was not a source of despair. It was the very reason scientific inquiry remains meaningful. If the universe were fully understood, curiosity would end. The adventure of thought would disappear. Instead, The cosmos offers an endless landscape of problems waiting to be explored. Human existence, therefore, acquires a strange dignity. We inhabit a small planet orbiting an ordinary star within an immense galaxy. Our lives are brief compared to cosmic time. Our bodies are fragile arrangements of atoms. Yet our minds can ask questions that reach across the entire universe. This capacity defines the human condition. Einstein believed that the search for understanding represents one of the highest expressions of freedom available to humanity. Material success fades, political power dissolves, civilizations rise and fall. But the pursuit of truth transcends generations. Ideas discovered centuries ago still illuminate modern science. The equations of long-dead thinkers continue to guide spacecraft and reveal distant galaxies. Knowledge becomes a bridge connecting minds across time. In this sense, the human quest for understanding becomes part of the universe's own unfolding story. The cosmos produced stars, planets, and eventually organisms capable of reflection. Through those organisms, the universe becomes aware of its own structure. Human thought becomes a mirror in which the cosmos glimpses itself. Yet this vision carries no comfort about the future of humanity. Einstein never believed the universe guaranteed human survival. Nature operates according to laws indifferent to our desires. Civilizations may vanish, species may disappear. The cosmos will continue without us. But the brief period during which conscious beings exist allows something extraordinary to occur. For a moment within cosmic history, the universe becomes capable of understanding itself. This moment defines the philosophical significance of science. Each equation written, each experiment conducted, each theory proposed represents a fragment of that self-recognition. The mind reaches outward into the structure of reality and discovers echoes of its own logic. But the deeper this exploration continues, the more the original questions return. What is reality? What is time? Can the human mind truly understand the universe? Einstein spent his life confronting these questions. His theories transformed physics. His doubts reshaped philosophy. His conviction that the universe must be intelligible continues to guide scientific inquiry. Yet even after all the equations and all the debates, the mystery remains. The universe continues to reveal fragments of order while concealing its deepest foundations. And as long as that mystery endures, the human search for understanding will not end. Because every answer once discovered quietly opens the door to another question waiting in the darkness. The equations changed physics. The questions changed philosophy. Albert Einstein did not simply rearrange the laws of nature. He forced humanity to confront something far more unsettling. Our understanding of reality is fragile. Our perception of time is deceptive. Our knowledge of the universe is always incomplete. Behind every scientific discovery lies a deeper philosophical rupture. We believed we saw the world directly. Einstein revealed that we build models. We believed time flowed the same for everyone. Einstein showed that time bends with motion. We believed space was empty. Einstein uncovered a living geometry
shaping the movement of everything. Each step stripped away a layer of certainty, and yet something extraordinary remained standing after all the illusions collapsed. The universe is intelligible. This is the paradox at the center of Einstein's legacy. The deeper science investigates reality, the stranger the universe becomes. Time slows, space curves, particles behave like probabilities. Observation itself appears entangled with the structure of events. Reality refuses to match common sense. But at the same time, reality continues to reveal mathematical order. The cosmos behaves according to principles that the human mind can slowly uncover. Equations written in quiet rooms describe the motion of stars across billions of kilometers. Abstract symbols predict phenomena that instruments confirm decades later. The universe answers the questions of reason. Why should this be possible? Einstein never claimed to possess the final answer. Instead, he lived inside the mystery itself. His work showed that knowledge advances not by eliminating uncertainty, but by confronting it directly. Science does not close questions, it sharpens them. What is time if it does not truly flow? What is reality if observation influences what we measure? What is the universe if space and time are part of one deeper structure? These questions did not end with Einstein's theories. In many ways, they only began there. Modern physics continues to wrestle with the same tensions that defined his life. Relativity and quantum mechanics still stand beside each other without complete reconciliation. The dream of a unified theory remains unfinished. The nature of consciousness and its relationship to reality remains unresolved. The search continues. And perhaps that is the most important philosophical lesson Einstein left behind. Truth is not a destination, it is a pursuit. Every generation inherits the questions of the previous one and pushes them slightly further into the unknown. Each discovery illuminates a fragment of the cosmic structure while revealing deeper layers still hidden. Human knowledge grows like a circle expanding into darkness. The more we understand, the more the boundary of mystery increases. Einstein understood this with rare clarity. His work transformed our image of the universe, but he never pretended that the transformation was complete. The cosmos remains larger than any theory that attempts to describe it. And perhaps that is precisely what gives meaning to the human search for knowledge. We are temporary beings in an ancient universe. Our lives pass quickly compared with cosmic time. Yet within that brief existence, we possess something astonishing: the ability to ask questions about the universe itself, to look at the stars and wonder what laws govern them, to examine time and ask whether it truly flows, to look inward and question what it means to know anything at all. These questions echo through the centuries because they reach beyond physics into the deeper structure of human existence. Einstein's legacy, therefore, cannot be measured only by equations. It lives inside the questions he refused to stop asking. What is reality? What is time? And perhaps the most unsettling question of all, can the human mind truly understand the universe in which it exists? No theory has yet delivered the final answer. The equations continue to evolve.
The debates continue to sharpen. The mystery continues to deepen. And somewhere within that expanding horizon of understanding, the same ancient curiosity still pushes humanity forward. The quiet, relentless demand to know what the universe really is.